this part of the respiration, which I'm hoping to finish it up today. So we talked about this part, the glucose, the breakdown of glucose to pyruvic acid is common to both respiration as well as is common to both respiration and fermentation. Today what I'm going to do, I'm going to catch up on this part a little bit more, but when during the process of respiration, is the glucose broken down to pyruvic acid, and that pyruvic acid can be channelized to the respiratory pathway. It goes through this transition reaction, Krebs cycle, and the electron transport chain. Or it is possible that this pyruvic acid, depending upon the genetics of the bacteria, it can just be channelized to the fermentative pathway. When there is fermentative pathway is the dominant one, it would generate a lot of acidic product, lactic acid, or the propionic acid. And we are going to catch up on that part because the Swiss cheese flavor, the cheddar cheese flavor is because of some of the fermentative end product. But this is the part what we discussed last time. There's a transition reaction when the pyruvic acid gets converted to the acetyl-CoA. It loses the carbon dioxide, and when you lose a carbon as carbon dioxide, it is called as decarboxylation. So there is no decarboxylation in the glycolysis pathway because the 6-carbon glucose is broken down to 2 molecules of the 3-carbon pyruvic acid. So there is no loss of the carbon atom, but then the pyruvic acid undergoes the decarboxylation in the transition reaction, and it gets attached to the acetyl group to form an acetyl coenzyme, which now enters the Krebs cycle. This Krebs cycle is a whole cyclical series of reactions. And the Krebs cycle in a bacterial cell, the transition reaction in a bacterial cell occurs in the cytoplasm, whereas in our body cells, the Krebs cycle occurs within the mitochondrial matrix. Am I correct? It occurs within the mitochondrial matrix, but because bacteria do not have the mitochondria, this whole transition reaction and the Krebs cycle reaction occurs within the cytoplasm. Once it occurs within the cytoplasm, during the Krebs cycle, there are a lot of intermediates. I don't have it in my slide checkout, but if you look in your textbook, there are a lot of enzymes, a lot of intermediates, which is over here, which obviously I'm not asking you to remember or to study these. There are a lot of acidic intermediates are being generated in the Krebs cycle. Like the malic acid, it says malic acid, citric acid, oxaloacetic acid, alpha-ketoglutarate acid, succinic acid, fumaric acid. Look at this. All these are the acids being generated in the Krebs cycle. You see? Now, one of the important part of the Krebs cycle is it generates again some of those reducing equivalent, which is the NADH and the FADH2. These reducing or the reduced FAD and the reduced NAD, what they do is they carry the electron to the first member of the electron transport chain. So during the hydrolysis of glucose, the energy which is released is put in these piggy banks, like FAD, I call them as piggy banks. FADH2 and NADH are like piggy banks. They bring in the electron with a lot of high energy to the first member of the electron transport chain. And as the electron moves down the electron transport chain, as electrons move down the electron transport chain, packets of energy, that potential energy is released in small packages, and that is basically harnessed to form the ATP molecule. So this is what is happening in the electron transport chain. The electrons are flowing from a high energy state to a low energy state, and as it is flowing from a high energy to a low energy state, it is releasing short bursts of energy. And that energy is successfully used to create the ATP molecules by the phosphorylation of an ADP to form ATP. How this whole process occurs, before we get on to this whole process, how ATP is generated in the electron transport chain, a few note about the Krebs cycle also undergoes decarboxylation. So guess what? The carbon dioxide, what you are exhaling, you are taking in the oxygen. That oxygen is only used in the last step of the electron transport chain. Not in the initial step, not in the Krebs cycle, neither in the transition reaction or in the glycolytic pathway. The oxygen, what you are breathing in, it is only used, that oxygen is only used in the terminal step of the electron transport chain. How cool is that? And the carbon dioxide, what you are giving out, that carbon dioxide is coming from two places. One is in the Krebs cycle intermediate, and the other one is from the transition reaction. That's the reason, because the oxygen what you are breathing in is converted to water. Even if you are not drinking any water, say you are being confined in a room, you are not drinking any water, but there is oxygen, but you still want to pee. Where is the water coming from? Where is the water being generated? You are not drinking any water because the oxygen what you are breathing in, that will be terminally reduced to water, and that's how your body is generating the water molecule. Is that cool? Now, to get a little bit more deeper, if I try to dig deeper into the electron transport chain, this is what I mentioned last time. And folks, again, in the respiration path, the terminal electron acceptor, if it is oxygen, it is aerobic respiration. If it is some molecule other than molecular oxygen, it is called as anaerobic respiration. So that fine line between aerobic and anaerobic is dependent upon who is the terminal electron acceptor. When you see the blackening in the butt area, that's because of the anaerobic electron acceptor. In the medium, it has the sodium thiosulfate as an artificial electron acceptor. So thiosulfate, once it accepts the electron, instead of forming water, it forms H2S gas. And that H2S gas, again, reacts with the iron sulfate to form the iron sulfide. Yeah, go ahead.
I wanted you to repeat what you said. If oxygen is the last
Terminal electron acceptor,
then it's aerobic.
It is always aerobic respiration. If terminal electron acceptor is oxygen, it is aerobic. If instead of oxygen, if it is some other inorganic molecule, remember inorganic is the important word. If it is any inorganic molecule other than oxygen, it is anaerobic respiration. We talked about nitrate, sulfate, carbonates. Those are all classical example of anaerobic terminal electron acceptor. Is that cool? Clear? Yes.
Is it the step of turning the pyruvic acid into the acetyl-CoA that's releasing the other carbon dioxide?
Yes, there are two times. There are two times the carbon dioxide is released. One is this time in the transition reaction and in the Krebs cycle.
Okay.
And that is called as decarboxylation.
The oxygen that is accepted as the last electron in aerobic, it's an inorganic oxygen?
It's inorganic. There's no organic oxygen. It's always an inorganic. Okay? Now, so there are many of these electron transport chain has certain members, and all these members of the electron transport chain, they are very closely approximated. They are very placed close to each other. Guess why are they placed close to each other? and why they are present on the membrane?
To let things pass by.
Hmm?
To let things pass by, pass in,
Good job.
permeable.
Good job. First of all, they are very they are close spaced to each other. They are very close in close approximation because it makes it easy for the electron to be passed from one member to the other member. Why are these not soluble protein? Why they are all attached to the membrane? Can you tell me that part? Why are they all attached to the membrane, and why they are not, why they are not present as a soluble protein or something which is just present in the cytoplasm?
They're big molecules.
Huh?
To monitor the ions passing, or
No, you're going correct. Tell me. Don't feel shy.
to monitor the ions that are to
Pumped
monitor
across the
polarity.
membrane.
Yeah, to pretty much monitor the polarity of the plasma membrane.
Good job. Instead of the polarity, you can say it maintained because the protons, once they are pumped outside, you maintain a gradient. There's an electrochemical gradient. Okay? So to maintain that gradient, these are all associated with the membrane and they are closely spaced to each other so that the electron can be passed easily from one member to the other member. These are the two main reasons why electron transport chain members are associated with membrane. They're closely spaced and they can create the gradient or the electrochemical gradient. Now these electrons, some of the members they act as proton pumps in the sense they accept the electron-proton pair. Obviously, the electron is passed to the next member, but the proton is pumped across the membrane. And when the proton is pumped across the membrane, you generate a gradient, which is more proton outside. Proton is outside, and it is more outside and less inside. And because of this, there is a gradient. A gradient is generated. And what we call this gradient, because of the proton pumping across the membrane, we call it as electrochemical gradient. We call it as electrochemical gradient. And inherent in this electrochemical gradient, there is a potential energy which is called as proton motive force. So there's an electrochemical gradient, and inherent in this electrochemical gradient, inherent in this is potential energy. There's potential energy, and that potential energy is called as proton motive force. That proton motive force is harnessed. That proton motive force is harnessed by, there's a potential energy, and this is harnessed by ATP synthesis. Does anybody know about the working of the batteries? The car battery or the battery that you use, in your anything, how does the battery work?
Positive and negative.
There are positive and a negative terminal, but then how does the battery work? Huh? It works on the same principle. It works on the same principle.
Oh, by transferring the electron down.
Yeah, it works on the same principle. See, you know too many things today. You know, like not only microbiology, you also know how does your car battery work. How cool is that? It works on the same principle. Battery works because in a battery there is always an electrochemical gradient is established, and once you try to nullify the electrochemical gradient, that potential energy is converted to electrical energy.
I was just wondering if we're supposed to know which of the different electron carriers, like NADH is coupled with, or which ones pump hydrogen.
I will tell you. No, I will not go with the which one pumps the hydrogen, which one acts as a proton pump. But it's very easy. You know, remember the flavor protein is the first one. The flavor protein is the first one, followed by the flavor protein is the ubiquinone, you know. So flavor protein is the first acceptor. Ubiquinone is the second one. The third one is the oftentimes, oh, this one is not. So oftentimes flavor protein is the first one, then there might be some iron sulfur protein, ubiquinone, and then the cytochromes are in all order. Sometimes there might be a flipping of the cytochrome orders, but usually it is cytochrome B to cytochrome C to cytochrome A or to A3. This is usually the order in most bacteria, but this is not a fixed one. Some bacteria may have a flipping of the cytochromes in the other way around, but this is the majority of the bacteria. I wouldn't say this is a hard and fast rule, but they tend to follow the cytochrome in this order. Okay. Now, getting into this part about the potential energy, so look at this, what happens. The electrons, I want everyone to be clear, folks, but this is easy compared to the cell wall structure. This looks like a turn off, but it is not. I love it. Okay? Now this one, look, the electrons are being transferred from one member to the other members, but as it is being transferred, some of them, they act as proton pumps. So what they're doing is, they're taking the proton, pumping it across the membrane. Once it is pumped across the membrane, those protons, they cannot just diffuse across the bilayer because that bilayer is impermeable to the proton. They cannot diffuse across the membrane. There are certain designated areas within the membrane, and only through those areas the proton can come back because you generate an electrochemical gradient. There is chemical is involved because the protons are chemical. There is electron, or the electrochemical is because there is a charge difference between the outside and the inside. So when I say there's an electrochemical gradient, it's electron. When I'm talking about electron, it's because there's more positive charge outside than inside. That's where the word electron is coming from. And there's a chemical because the proton is a chemical compound. So there is an electrochemical gradient is now established across the membrane, and that electrochemical gradient, which has more proton outside, less proton inside, there's a lot of potential energy is now generated. And that potential energy can only be utilized when the protons are trying to flow back inside, and that's when it tries to flow back inside. In those specialized chamber associated with it is the ATP synthase. The ATP synthase harnesses that potential energy of the proton motive force. And once it harnesses that energy of the proton motive force, it allows a phosphorus atom to be conjugated or to be linked to an ADP to form ATP molecule. But all that energy, when it is coming in, that energy is utilized to add up another phosphorus atom to an ADP molecule. Remember, this is a negatively charged phosphorus, this is a negatively charged phosphorus. I showed you last time when there is a negatively charged phosphorus trying to bind to another negatively charged phosphorus, there's so much of repulsive force has to be overcome. But once it binds and it forms an ATP molecule, when the phosphorus is broken down, an equivalent amount of energy is released. So this is how the whole process of ATP formation occurs. A major part of the ATP is utilized for bacterial motility, for the transport of nutrient across the membrane. Much of the ATP which is generated is being used up. And this whole process is also called as the chemiosmotic theory. So this whole process, these terms get very close and they get mixed up. But if you try to say, it's called as chemiosmotic theory for ATP generation. It's called as a chemiosmotic because chemicals are involved. Osmosis, just like osmosis, where there is a gradient of water molecules across the membrane, here you have a similar gradient of the electrons across the protons across the membrane. So it is called as electrochemical gradient across. So it is called as a chemiosmotic theory. A few things before I catch up on your explanation. In some bacteria, this ubiquinone, which is so ubiquitous in all living organisms, that's why it is called as ubiquinone. In some bacteria, this ubiquinone is a menaquinone. Menaquinone, just by a few step reaction, it can generate vitamin K. E. coli has, instead of the ubiquinone, E. coli has the menaquinone. I think I did mention it last time. Am I correct, folks?
Yes.
E. coli has menaquinone. And that's the reason why E. coli is the one that can make up the vitamin K, can supply our vitamin K requirement. Other bacteria fail to do that because they do not have the menaquinone. They have the ubiquinone, and from the ubiquinone to vitamin K synthesis is a lot more step. It's a lot more steps, and the other bacteria cannot do it. With the same note, some bacteria, the cytochrome A and the cytochrome A3, these are both complex together. These are complex together, and when these cytochrome A and A3 are present together, it is called as cytochrome oxidase. So when these, what's the time? Oh Lord.
Break time?
Yeah, can I just catch up one quickly on this one and then I'll stop it. So in many bacteria, the cytochrome A and A3 are complex together, and when they are together, those are called as cytochrome oxidase. Those are referred to as cytochrome oxidase when they are complex together. We will be doing this experiment on the last day to see some of the bacteria that you're going to isolate from your throat. Are they oxidase positive or oxidase negative? So when you come back from the break, I'll give you some more example of the oxidase positive and the oxidase negative cell, and we'll go from there. Alrighty, folks? Yes, you want to come to check it out after break? Huh? So everybody can get it. So we'll take about like a few minutes break at about 7:15. Come back. Come back around about 7:15 and then we'll go from there.
Pardon me, sorry. Thanks, dude.